Okay, so we'll continue with the type definitions. So far we've only played with the terms and with types, but we haven't seen how to introduce new types. So for example, how to define the type of natural numbers, right? And so in Lean, everything is built from first principles. So in the core of Lean, there are no natural numbers. Somebody had to define them. And so on. So the language is quite poor to start with, and then it's enriched by the users or by the core libraries. Okay. And these types, so we call them inductive types, but they're also called inductive data types or algebraic data types or just data types. So I'll try to stick to the phrase inductive type, but if I end up using another phrase, please don't be too confused. For our purposes, these are all the same thing. So we start with the natural numbers. So we work in our own namespace called mynat to avoid any conflict with the standard natural numbers. And then we define a type called NAT. And the command is called inductive. And that creates the type, that declares the type. So the syntax is inductive, the name of the type, followed by colon. And then just to be sure, we write type again with a big T. And then we specify so-called constructors. So in this case, 0 and successor. So 0 has type nat, so it's a natural number, it's a constant. And suc is a function from nat to nat. It's a successor function, right? So we've said, basically, we have this new data structure. It has two possible states. It can be in state 0 or in state suc. And when it's in state suc, then it needs an argument, which is itself a natural number, which is either 0 or suc, right? So in that way, you can represent all natural numbers and nothing else. But notice that this is quite high level. You know, this is much more high level than what you do in C or C++. And it's also less verbose than what you do in Java. So if you want examples of how to do the same thing in Java, please look at the Hitchhiker's Guide, because I worked out an example there. Okay, and then we can use check to check the types of various things, right? So here, you know, nat is a type, nat 0 has type nat, nat suc has type nat to nat as expected. And outside the namespace, then we have our good old nat. So this is the old natural number with the fancy syntax, even a syntactic sugar, right? Which has attribute 124, whatever that means. Okay, let's look at a second example, arithmetic expressions. And this is the example that's worked out in the Hitchhiker's Guide. So here, of course, Lean has, you know, addition and multiplication and so on already, so you don't need to define that. But nonetheless, we can we introduce our own type of arithmetic expressions, because maybe we want to program a calculator, right? Or maybe an arithmetic expression simplifier, or maybe even the programming, you know, programming language and programming language syntax and interpreter. And then we need to model these things, you know, as data structures, right? So we want a data structure here to capture an arbitrary, well, not completely arbitrary, but arithmetic expression, which can be either an integer, right? So num takes an integer and returns an arithmetic expression. So it just embeds an integer in the new type. Var embeds a string, which gives the name of a variable. Add takes the sum of two expressions and returns an expression. And then you have three more similar operations. So I can show an example here. I could say a exp num of 5, and that would work. But I could also say a exp add. So I want to add 5 to the variable x. Then I would write it like this. And then Lean just prints that. So of course, these are arithmetic expressions only in our heads, right? There's to Lean, there's nothing that says that add is addition, that sub is subtraction. These are just 6 names for 6 fields and so on. So it's abstract nonsense for Lean. But typically we would end up implementing a function, evaluation function, that would take an arithmetic expression and a context, for evaluating variables, and that would return an actual value. And then we would give an actual semantics to these constructors. Then the type of lists is very important. It's the, I mean, if you've programmed ever in Haskell or even in Lisp, you end up having lists all over the place. So a list is a bit different because it's polymorphic. That means it has a type variable. You can have a list of natural numbers, lists of natural numbers, you can have lists of integers, lists of functions, and so on. And that is a parameter here on the left of the column. So that's just the syntax. So it's a list of alphas. And these alphas are types. And I think you can remove many of those annotations. Well, maybe not this one, but often we're very explicit. Maybe we can remove this one. Yeah, we tend to be very explicit in the course just to, in the interest of learning. And then we have 2 cases. Nil is simply a list, and const takes 2 arguments, an element of type alpha, right? You have a list of apples. Well, this is where your apple comes in, and a list, and that creates a new list. So this is called the head, and this is the tail. And you can build longer and longer lists by, adding const and, adding elements or apples at the front of your list. I'll show examples later. And then notice one thing. It would be very tempting to write list alpha here everywhere. And indeed, in some programming languages, you would have to do it. But in Lean, you have the rule that if you declare a parameter here on the left-hand side of the column, then that parameter is implicit throughout the entire definition, and you're not even allowed to specify it. It is fixed. I mean, this really defines list alpha. So from then on, you just write list, and it's always going to be alpha. But this is only for the scope of the definition. Afterwards, we'll have to write the alpha. So if we look here, what's the type of list? Nil. It's list of something. We don't know what this is, but doesn't matter for now. Const is the same thing, right? So these are just kind of variables that stand for no known type. But you see now list const takes a list that has an argument here because we're outside the declaration. And list also exists in the real library, and we see this is even the definition. And then when we see output like this from Lean, then we might want to panic because what is at X core, blah blah blah, and then a few lines below, what are those capital Pi's and those curly braces? I mean, to be honest, I only understand half of it. So what does this mean? It means don't panic. So if you know the Hitchhiker's Guide to the Galaxy, right, the novel, it has, in the novel, there's a book that's called The Hitchhiker's Guide to the Galaxy, and that has in big letters the text, don't panic, right? So if you're hitchhiking across the galaxy, the first rule is not to panic. And here's the same thing with Lean. You will see things that you don't immediately understand. Sometimes there will be weird syntaxes in the output that we haven't taught, and the advice is, take a deep breath, take it with a sporty attitude. Things are going to be all right. And you can ask us on Canvas, of course.